So after solving for I2b and I2c and adding the two integrals means finalizing I2, I will have to write the solution of I2 as it comes out that I2 is finally equal to 8 over pi a cube over 8. So this is pi a cube over 8 r1, and this is 1 minus 1 plus 2 r1 over a and e to the power minus 4 r1 over a. So we have converted the r2 integral into r1 by putting the limits r1 there. So I2 comes out to be this. Now we will put this I2 that we have calculated over here in this one, and all the integral will be converted into R1, and then we will integrate with respect to the d cube R1. So our expression becomes is VEE, the electronic repulsion term is E square over 4 pi epsilon naught, E square over 4 pi epsilon naught 8 over pi a cube, and then the whole integral, and 1 minus all this, 1 minus 1 plus 2 r1 over a e to the power minus 4 r1 over a, and this is from here, this is whole integral, and this one, let me use the square brackets here, and then e to the power minus 4 r1 over a, because 1 e to the power minus 4 r1 over a comes in I2, while 1 minus 4 r1 over a is still in this integral, because R2 we have converted. So this, and then d cube r1, so d cube r1 I can write is r1 squared sine theta d theta. Okay, so 1 r1 from here, 1 r1 square will come here, but that we have simplified already with this r1, so we will have only r1, and then d r1 sine theta 1 d theta 1 and d phi 1 here. And as usual, now the angular portion here, the sine theta, d theta and d phi, this will as usual give 4 pi, the solid angle, and the rest of the integral when we will solve all this integral. Now what this integral is, it's a lengthy integral, because here we are having r1, it will be multiplied with all this, this will be multiplied with this, so it will become minus 4 r1 and minus 4 r1, it will become minus 8 r1 over a. We will solve this integral and you will get the lecture notes, and in the lecture notes this integral I have solved step by step, and this integral comes out to be equal to, this whole integral comes out to be equal, the VEE terms comes out to be 5, the integral portion over R1. Okay, the integral portion over R1, it will means the integral will only give us the integral over R1 will give us 5a squared over 128. So we can write our VEE to be equal to e square over 4 pi epsilon naught and then 8 over pi a cube. Then we have the 4 pi, okay, from this 4 pi this one, and then the integral over R1 gives us 15a square over 128. 5a square over 128, and we are going to simplify this one as we see that 4 when multiplied with this gives 32. 32 with this one simplifies, and 32 with this one, if I multiply with 4, so 4 will come in here, then 4 here, and we have the pi simplification here. The a square will simplify with this, so I will get the result of VEE is equal to e square over 4 pi epsilon naught, and 5 over a remains there because 5 here and then a here remains, while the rest of it they simplify. And now because it will all simplify, and now as we also know one thing, that the e square over 4 pi epsilon naught, the e square over 4 pi epsilon naught 1 over a is equal to minus 2e1. This is one of the result we know from the Bohr radius calculation. Energy and radius are related with this, so I can write, means looking back to that equation, e square over 4 pi epsilon naught and 1 over a is there, so I can write that this thing I can write from equating with that thing is minus 5 over 2, because I write it in terms of E1 because even I know this is 13.6 electron volt, and this is equals minus 5 over 2 E1, and putting 13.6 here, it will make our VEE is, because this is minus and minus here, so become plus, equal is 34 electron volt. So our Hamiltonian, which we have calculated earlier without the electron repulsion term, that was minus 109 electron volt, and now we have this VEE is 34 electron volt, and then the H will come out to be equal to minus 75 electron volt, because 9, 4, 5 and 10, 3, 7. So we went closer to the experimental value, which is minus 79. So this value is even closer to the experimental value. And what thing we did here, and that resulted in our closer approximation, just calculating the VEE terms, the electronic repulsion term or electron repulsion term. We went even closer to that one, and we can even do better if we do more corrections to the Hamiltonian. So the next that we are going to correct our Hamiltonian is the kinetic energy term, the potential energy term, but we will focus on Z, because what we are actually doing, if we look closely to this thing, we are using the hydrogen wave function. Now the hydrogen wave function, it's just like, means the wave function we have written just like two hydrogen atoms, or trial wave function. So the two hydrogen atom and the Z is coming in there is equal to 2. Now in helium the Z is equal to 2, but here the situation is different. Here the two protons are inside nucleus. They are not like individual protons. So in the next lecture, we will be basically focusing on Z. We will optimize Z, and then we will see that even ignoring the fine structure or the hyperfine structure, we will go much closer to the experimental value within a range of just 1.5 electron volt, because here now 4 electron volt difference is there, but we will minimize this difference to just 1.5 electron volt. And then after that, if we include all the details, then that 1.5 electron volt will be covered as well, because these are very fine details that are to be included. But as per this course, we will only focus on the optimization of Z, and we will do calculate the value of Hamiltonian in that situation.